All right, good morning, everyone. Let's go ahead and look at the next um, set of videos for today's date of March 5th. Um, Let me get that PowerPoint ready to go here. Okay, so let's see, just one sec. All right, so we're going to look at mutually exclusive events, and we'll see how they're a little bit different from um, complement complementary events. So, uh, and I do need to clarify. So, to make calculating probability easier, we want to identify any special relationships between events. For example, if we're asked to find the probability that a triathlete is both riding their bike and swimming at the same time, we should be very skeptical. Um, A and B are mutually exclusive events if they cannot occur at the same time. Okay, so the one way to illustrate this is with a Venn diagram, and just to clarify, um, and I'm not sure I was probably as clear as I could have been in the previous video. So let me try to do that here. So we have event A and we have event B. So I'm gonna label this A and I'm gonna label this B. So those are mutually exclusive events. So so if you're taking notes, you might want to make that a note. Um, and the clarification I want to make is that Um, A is the thing, or the event is the event that is shown by the circle that's labeled A. And what I'm shading now is A prime. So, and I should have actually kept going there. That's where I want to be clear. A prime includes B. So that's the subtle difference between mm, events that are complements of each other. That's A, which is inside the circle, and A prime, which is everything in the striped area. Everything in the striped area that includes B and things that are not in B, but everything that's in the striped area, that's A prime. So those are complements of each other and they make up um, 100% of the 100% of the outcomes. 100% of the outcomes. But the probability of A might be like um, let's say 1/5, and the probability of B might be 2/5. Oops, 2/5. Okay, but that only makes up 3/5 of the outcomes. Then there's the stuff inside the universal set, right? Which would be the remaining the remaining 2/5. Um, But so a prime would be made up of B and things not in B, but that are also not in A. So hopefully you can decipher my words and then try to make sense. Okay, so um, this now they're showing overlapping events here, but there's nothing in the intersection. So they might as well have made these two circles apart from each other. Just consider the Venn diagram above. Event A has 1, 2, 3, 4, 5, and event B has 6, 7, 8, 9, 10. So we say A and B are mutually exclusive. There's nothing in the intersection. And actually, if we were to draw these, we would not draw anything, we would not draw them overlapping in any way, even though they've done it that way. But really key is that the probability of A and B is zero. There's nothing in the intersection. So that's how you know that's key to knowing whether two events are mutually exclusive. So if you're taking notes, that would be something you want to write down and connect it with mutually exclusive events. Um, if possible outcomes were 1, 2, 3, 4, 5, and the possible outcomes for B were 5, 6, 7, 8, 9. So A is 1, 2, 3, 4, 5, and B is 5, 6, 7, 8, 9. So now we did put something in the intersection, which is a 5. So the probability of A and B is not zero. So that's how you know that they're not mutually exclusive. So that could be used as a test to determine whether or not things are mutually exclusive. Okay. If it is not known whether A and B are mutually exclusive, assume they are and they are not until you can show otherwise. Um, the following example illustrates these definitions. You have a fair, well-shuffled deck of 52 cards, consists of 4 suits, clubs, diamonds, hearts, and spades. There are 13 cards in each suit, consisting of 2, 3, 4, 5, 6, 7, 8, 9, Jack, Queen, King, and Ace of that suit. Given events A and B are the two events mutually exclusive. So choosing a Jack. Okay, so you're looking at all 52 cards. So event A is choosing a Jack. So you're gonna have uh you can show the 4 suits. Let me see if I can do this. It's not the easiest thing to draw. I have to make sure I have to try to draw it. Let me see. Um, so those are the that's not gonna work. So let me try that again. I think I have to make those larger because they so let me try this. Yeah, I'm not sure this is the best way to do it because it's extremely messy. But there is I think one area where they all overlap, and that's here. That's where all the jacks might lie. And then choosing a card in the spades suit, choosing a card in the spades suit. So that would be, let's say it would be let's say this is spades. So I believe those are not going to be mutually exclusive. Um, and from the picture, you can see that some of the jacks are inside the spades. So the and part, you could be a jack and a spade. And so they're not mutually exclusive. Let's go ahead and read. Possible outcomes for event A are Jack clubs, Jack of diamonds, Jack of hearts, Jack of spades. Possible outcomes for event B are 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, A. On spades, these events are not mutually exclusive because they share a possible outcome, the Jack of spades. Okay, so that's the more plain language way of explaining that. Given the sets, even numbers, all even numbers, and all prime numbers, uh, are A and B mutually exclusive. So um, the evens are think those are pretty easy to just list. It says 2n. That might be a little confusing, where n is an element of the counting numbers, which are one, two, three, etc. So they kind of sneak that technical language in. So the idea is that any number multiplied by two is an even number. Uh, and it's important for defining the set, but for what we're looking at, we need to also be able to define the prime numbers, which is anything that's divisible by one and the number itself. And it turns out that two is the only even prime number, but it's a prime number. The other ones are odd, but because two is in both sets, the sets are not mutually exclusive. Okay. You have a fair well shuffled deck of 52 cards. It consists of four suits, clubs, diamonds, hearts, and spades. There are 13 cards in each suit. 2, 3, 4, 5, ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. Um, are events A and B mutually exclusive? So they're defining them this way, choosing an eight. So basically, it's a set. Uh, you could use a Venn diagram, but it's a set that has uh, four things in it, right? The eight of clubs, eight of diamonds, eight of hearts, eight of spades. Okay, so they list that down here. So um, and then the other one is choosing a jack of hearts. So there's it's a set of one thing, a jack of hearts. Well, a jack of hearts cannot also be an eight of hearts. So the intersection is empty, and also the probability of being an eight and a jack is zero. So they're definitely mutually exclusive. Okay, so that brings us, so that's mutually exclusive events. If probability of A and B is zero, that's a good test for knowing that two things are mutually exclusive. Then there's the addition rule. The addition rule, really key, um, but I think it's actually, so they're leading us to, so we already looked at the addition rule. Um, And that is when you have, well, it works for events that have an intersection, but it also works for events that are mutually exclusive. So let me read. The addition rule allows us to calculate the probability of event A or B by adding their probabilities together and subtracting the probability of both events occurring. We talked about this. You don't want to count something twice, so you remove one of the repeated, one of the each repeated outcome, you remove it. Um, Anything that happens in A and also happens in B, you want to remove it. So anything in the intersection, you only want to count this once, right? Now, if they're mutually exclusive, then you don't have to worry about this piece because there is no intersection. And that's what we're looking at here. Okay. So, and excuse the text here, but it says, let's look at some examples using both versions of the addition rule. So for example, in the above Venn diagram, event A has outcomes 1, 2, 3, 4, 5. I'm sorry, 1, 2, 3, 1, 2, 4, 5. The event B has the outcomes 5, 6, 8, 9, 10, 12. The event C has 3, 4, 7, 10, 11. So let's see what they ask us. There are 12 total outcomes, and the probability of A is 4/12, which is a third. So if you count, there's one, two, three, four things in A, and there's 12 total things. So, and then the probability of B, you just count how many things are in that circle. Probability of C, you count how many things are in that circle out of the total. And the important thing, you add up you add the probability of A, that's what they're asking for, probability of A or B. They're not asking you to consider C. And then you have to subtract out the thing that you count twice. So the thing that you'd be counting twice is the 5, which occurs in A, and then it also occurs in B, but you only want to count it once. So that's the 1/12. And that's how you end up with the 3/4. Okay. So we've already done that uh, in this class. Let me uh, not belabor the point. So here they're going to ask us the probability of A or B, and the thing to notice is that there don't appear to be any common elements in A or B, right? There's not a 1 down here. There isn't a 2 down here. There isn't a 4 or an 11, and vice versa. There isn't a 5, there isn't a 6, there isn't an 8, there isn't a 9, a 10, or a 12 that appears in B that also appears in A. So they're mutually exclusive. That means P of A and B is 0. And so we go with a simplified version. You don't need the minus probability of A and B piece. So you just uh, figure these out alone, add them, and you get your answer. So that's the addition rule for mutually exclusive events. And this one just has values without a Venn diagram, um, or without an explanation of where the events came from. But it says Klaus is trying to choose to go to where to go on vacation. His two choices are New Zealand and Alaska. So you can't be in New Zealand and at the same time be in Alaska. Okay, so then what are we looking for? Um, what is the probability that he chooses New Zealand or Alaska? So you just add them. That's just the formula. Uh, they don't add up to 1. They add up to 0.95. So there must be a 5% chance that Klaus goes either somewhere else or that he sits on his couch. Uh, so this is a probability that he chooses New Zealand or Alaska, and there's a 5% probability that he chooses to go uh, not anywhere or something else. Okay. And this is so whenever they ask for probability of this or that, remember the or means you combine the two sets and you're looking for the key word. Well, you're either looking for the keyword that tells you the phrase mutually exclusive or the situation is is hopefully clearly or obviously a mutually exclusive situation. Karen wants to either take the subway to work or take a cab. Can't be on the subway and at the same time take the cab. So it's implied that it's mutually exclusive. So you're looking at this type of situation where the circles don't touch, and so you